Hi, my name is Nicki Driscoll, and I beat the often path by building new types of electronic devices to interface with the body, trying to help us understand the brain and develop new therapies for the brain using bioelectronics or devices that can interface with the brain.
Nicki Driscoll, PhD, is a postdoc researcher at MIT and CTO of NeuroBionics, a company that has developed a new kind of neural interface using microscale, flexible bioelectronic fibers that seamlessly integrate with the body. What the heck does that mean? Well, have you ever seen a fiber optic cable? Imagine a tiny strand that is as thin as a human hair. Each fiber integrates a range of functions such as electrical, chemical, and optical capabilities to sense and modulate the biological environment. Still confused? Well, I kind of am too. This tech actually gives us an unprecedented access into the symphony of a properly functioning brain, something that we'll talk about in this episode that is just ultra cool, and also a better understanding of the brain when it's not functioning properly, aka the symphony is playing out of tune. This is the kind of stuff that the sci-fi future is made of, but it's real life and it's here right now with NeuroBionics. This is going to be such an awesome episode. Here's Nicki Driscoll. I'm Ross Palmer, and this is Beat the Often Path. Well, that is awesome, Nicki. I'm so honored to have you on this show. There's been a lot of stuff in the media about these brain-controlled interfaces. There's a lot of controversy, actually, Elon Musk's Neuralink being the most notable example that people know. I don't know if you saw this article that came out recently of monkeys that apparently, were killed with Neuralink implants and scratching and clawing at the place where the chip was implanted. And some people are saying, is this ethical? Is it not? And I know this has nothing to do with your world, but I think people are generally both excited and apprehensive about brain control technology. So how did you get involved in this? And are you more excited about the possibilities or scared about what it might mean?
Yeah, so that's a great question. Lots of elements there. I suppose I'll start by talking about how I got into this space, and then I'll kind of circle back on Neuralink and neurotechnology in the news, because I think that there's a little bit of insider's perspective there and some comments on that. But in terms of how I got into the space in the first place, I was an undergraduate at Brown University, which happened to be one of the universities that was pioneering brain-computer interface technology along with Stanford. I knew nothing about BCI, brain-computer interface, BCI technology at the time.
I know this from our mutual friend Ramses. Yeah, he told me that.
Yeah, exactly.
BCI is a part of my lexicon now, just so you know.
Yeah, so I was studying bioengineering at Brown, and I was also really interested in the brain. I knew that I wanted to do engineering, but I had always been really fascinated by the brain and how much we still didn't know about it. So I took an intro neuroscience class at Brown, and they showed a video of one of the early BCI subjects who was able to control a robotic arm with her brain-computer interface. And it was the first time that she had been able to independently give herself a drink since she had suffered a brainstem stroke several years before. She was completely paralyzed and unable to communicate. And that just blew my mind. And I was immediately like, wow, okay, this is such a cool area of technology. It has so much potential to help people who are suffering with paralysis and other issues where there really are not good treatments right now. So that was kind of the origin story. I was immediately hooked and wanted to get into that space. So I started working in some neuroengineering research at Brown as an undergrad, and then continued that work doing a PhD at Penn, where I was building soft and flexible devices to interface with the brain. And I'll come back to that in a bit, but I guess to kind of talk about today's state of neurotechnology, yes, folks are probably hearing a lot about this in the news, very much driven by Neuralink, which is Elon Musk's company. I have some conflicting thoughts about Neuralink. I mean, I think they've done some fantastic work. A lot of their innovation has been on the surgical robotic side, and actually how can we implant a bunch of independent electrodes into the brain relatively quickly? So they've done some fantastic work there. I think what's a little tricky about Neuralink is, Elon Musk likes to approach this with like a tech entrepreneur's perspective, which is go fast and fail, go fast and break things.
Right.
And that works in tech, but when you go into something that's in the medical space, medical device space, that can be very problematic, right? Because you can run into issues of
Because the things are animals or people.
the things
in that
are
case.
lives, yes, animal
Right.
lives, people lives. So there is a different level of care and scrutiny and robustness that needs to be taken to every step of the process when you're developing something that's going to go into a living organism. And I think that to a certain extent, I think Neuralink has gotten some bad press, but yes, I think there was a lot of pressure on them to go really fast and meet milestones. And because they had that pressure, it's not clear that they were always having the highest level of protection and care for the animal subjects that they were testing. But I think that they've done a really good job of trying to address that and make sure that they're being more careful going forward.
Yep, I completely agree. And just for the record, I'm neither a hater nor a fanboy of Elon Musk. I think, pros and cons. And I've been reading his new biography from Walter Isaacson, and you really get a very detailed picture of the complicated individual that is Elon and all of the good and the bad, of which there are both. But
there is certainly both, and I think Neuralink echoes that also. Like,
right, exactly.
I have
like the concept is good, but
yeah,
is this the only way to execute on that? But so we've featured a couple different people who've done stuff with the brain, because again, to me, and I think let's take one of the things, since he is famous, Elon's reason for getting into Neuralink was changing the bandwidth, and the reason you described, of course, for getting into it yourself is similar, because we know that in terms of how fast I can type, as somebody who can type, or people who can't type, or who have, I think, cerebral palsy or various other types of disabilities that they might have, something limits the data flow between their brain and the real world. And of course, the desire to increase that data flow from either 0 to something, or from 100 bits per second to several megabytes per second, it's a very tempting thought, right? To be able to more directly communicate. I mean, I, for one, have tendonitis in my arm from typing all day, because that's my job, is to type 14 hours a day. So there is something that's very tantalizing about, could we remove these barriers and just more directly engage with the world around us? And some people have done this in a way, Neurable puts headphones on your brain and listens to your brainwave activity. Neuralink says, let's embed a wireless chip inside of your head. And you've got yet another completely different concept of how that might be possible, one that I'm just blown away by. So how did you come up with this specific idea, and what is that idea?
Yeah. So to back up just a little bit, I think that most of what you were just talking about is traditional kind of brain computer interface, where the idea is, let's record neural activity and extract data out and use that to control something, a computer screen, a cursor, a robotic arm, etc. And there are both invasive and non-invasive ways to do that, right? So Neuralink is, let's have a surgery and actually implant something in your brain. Neurable and many other startups that are working with EEG, so that's something that's placed on your scalp, you don't need to have any sort of a surgery, have been pushing in terms of what kind of data can we extract from the brain non-invasively, and then use that to help people, to augment them or allow them to control different systems. And I think that there's so much excitement in that world. We're actually a little bit on the flip side. So we're not necessarily working with data that we're recording out of the brain. We're actually directly delivering therapy into the brain. And we're doing that with electrical stimulation. So, there's kind of two fields here: record data out or stimulate to send things in. So the therapy that we're actually working on is deep brain stimulation. So this is a therapy that's actually been around since the 90s. It's used really widely for Parkinson's disease to help alleviate tremor and other motor symptoms. And it's also used for epilepsy, dystonia, essential tremor. So that's, it's an established therapy, but the trick is, like, you still need to have this very invasive brain surgery. You have essentially a rod of electrodes implanted down through your brain into a really deep region. And so my background is as a bioengineer, thinking about how can we make new kinds of devices to really improve healthcare and meet some unmet needs. And we're looking at this space thinking, okay, DBS works really well. This therapy, is very well established, but it's so invasive. You need to have this very invasive surgery. So there's actually very few patients who will elect to get it, usually only those who have the most severe symptoms. And so we started thinking about, is there a way that we could make this simpler and less invasive? And Ultimately, the approach that we're taking is we have developed something called a bioelectronic fiber. So this is a device that's about the size of a human hair that we can guide in through the blood vessels up into the brain. So you can think about this as being sort of similar to how a stent might be placed in the brain or how a catheter might be kind of threaded up into the brain to treat a stroke or an aneurysm. We use a similar approach, but then we deliver this device into the target brain region where it can deliver targeted electrical stimulation. So we're kind of early in the stages of pushing this technology out of the lab and into the clinic, but we're really excited about the potential that it has because ultimately our goal is to make deep brain stimulation much less invasive, and we hope that that'll expand access to the therapy to a lot more patients.
It's just, I mean, it's wild to even begin to hear that. For the ignorant among us, myself definitely included, what is the actual procedure then of inserting this? And for the people who haven't seen the video yet, we'll put it on the screen, but it's a human hair, like a fiber optic cable, I guess you could say, but even perhaps thinner than a traditional fiber optic cable. So how would that be inserted then into somebody's brain?
Yeah, so this is done in a catheterization lab or a cath lab. So it's different in that it's not an actual open surgery. These cath lab procedures are often outpatient procedures. And essentially, the way that it works, not to get into the gory details here, but they would enter through a blood vessel, usually in the arm or the femoral artery through the leg, or they can even go in through the jugular in the neck. They make a small incision into the artery or vein, and then they thread a catheter up into the brain through that pathway. And this is all done under fluoroscopy guidance, which is a form of X-ray, so they can see where the catheter is at all time and navigate it to the target region. And so with our device, we're essentially going to use existing catheters that are already routinely being navigated into the brain and just deploy our little hair-thin fiber device through the lumen of that catheter. So we can use kind of existing technologies to get our device there and then just deliver it into the blood vessels.
That's just, it's wild. It's so cool. So the electrical stimulation that you provide and the established tech, how does that work? What is the mechanism there, and why is that effective against things like Parkinson's?
Yeah, I'm glad you asked that question because the kind of funny answer is that DBS, deep brain stimulation, has been around since the 90s, and we actually still don't fully understand why it works.
I was going to say you're adding a new acronym to my lexicon. Now I know what DBS means. I learned BCI.
Yes.
Now I'm going to figure this one out. Okay.
Yes, DBS, deep brain stimulation. So it's kind of a funny story how DBS came to be. I think it was a little bit of an accident in the early 90s where they found that electrically stimulating these specific regions could eliminate tremor in patients with Parkinson's disease and essential tremor. And it was more or less an accident that they discovered that, and they started using that to their advantage for the therapy. And since then, there's been, 30 years of research to try and understand what is electrical stimulation in those brain regions actually doing. And we still don't have a totally clear answer for that. We know that it works.
Somebody put a fork in a toaster?
We still don't totally know why.
What's the
Sorry?
accident? Somebody put a fork in a toaster or something? How does this accidentally
No, I
occur?
think it was a tumor resection surgery or some version of a patient was already having a brain surgery, and they were testing some stimulation while they were going in.
Okay. So it was deliberate, but they just didn't know why they were doing it. Okay.
It was deliberate. I think they weren't totally sure what the effects would be.
Okay.
Yeah.
Okay. So providing this, what did they notice then? So we don't know how this works, but what happens when you apply that kind of stimulation?
Yeah, so when you're applying electrical stimulation into the brain, essentially all of your brain cells, your neurons, respond to electric fields. So when you deliver electrical stimulation at specific frequencies, you can drive certain neurons to become active, or you can inhibit neurons and actually prevent their activity. So for deep brain stimulation, when we're thinking about Parkinson's disease and tremor, there's a specific rhythm in the brain called a beta oscillation, which is pathologic, and that's actually linked to the tremors and the motor symptoms. And what this brain electrical stimulation does is actually inhibits that oscillation. So it stops the neurons from producing this kind of pathologic rhythm that causes the tremor. And so you can think of it as kind of like a jamming signal, right? We're kind of like disrupting this pathologic activity.
Wow. So is it somewhat related to the concept of music? I mean, frequency am I crazy in thinking of music right away when you bring this up?
No, not at all. I actually love that analogy. We love to make an analogy that the brain is like a symphony orchestra, right? You've got
Right.
many, many different frequencies of activity all happening at the same time. All the different violins and the cello and, all playing at the same time. So you can think of the brain as a little bit of a symphony of activity, and there's all these different frequencies that are happening at the same time.
And you could think of it like one member of that symphony is just playing wildly out of tune in the wrong rhythm, the wrong chart, for example. And you say, hey, we're going to go and just somehow deal with that part without messing up the other parts of the symphony.
Yeah, that's a great way to put it. I think it's you could think of it as like one person playing wildly out of tune, but then all the people around that person also start playing out of tune because it spreads. That's something that like in the brain you have these pathologic oscillations, and a lot of time that can recruit other areas of the brain to also start having this pathologic activity. So that's also, this gets into like seizures and this pathologic activity spreading through the brain. But yes, you can think of it like someone starts playing a bad tune and then it kind of affects the people around them. And what we can do with stimulation is try to silence that and get back to the natural rhythms.
Well, people often say that ignorance radiates out of me like a wave, a shock wave. The more people who are around me, the greater the field of ignorance. So I can relate to that analogy. But is this the reason why Parkinson's and other diseases get progressively worse over time? It's because one thing starts playing out of tune, and then as that radiates, it starts getting progressively worse over years and decades if it goes that far?
Yeah, definitely. That's definitely part of it. So, with Parkinson's and many other neurological disorders and neurodegenerative disorders, it is a kind of a spread of pathology, both in terms of like you can think like the frequency, the rhythms of what the neurons are doing, but also there's things that are happening more on the molecular level. So, in Parkinson's disease, we have death of specific type of neurons that are producing dopamine. That is kind of the hallmark of Parkinson's disease. And you also have the formation of these misfolded proteins that kind of accumulate in the brain and create these plaques. So those are both more on the molecular level but they do tend to like start in one region and then spread over time.
So then, does this treatment have anything to do with that? Is there a knock-on effect that it will also help prevent that spread, or are these really just two totally separate things we're talking about?
So we think they're two separate mechanisms. They're related, but at this point with electrical stimulation, we're pretty much only disrupting the like aberrant neural activity, and we're not really doing anything to treat the misfolded proteins or the cell death. So it's tricky. This is one of the reasons Parkinson's has been so hard to treat for so long, is that there's a lot of different things happening, and it's really not been possible yet to come up with a single therapy that kind of does everything. So what deep brain stimulation does, it treats the symptoms, it treats the motor tremor, but it doesn't necessarily treat the underlying pathology of dopamine neurons dying and the formation of these plaques. And that's actually why there's been a lot of interest recently in some new drugs that have come out that decrease some of the misfolded protein accumulation, although they've had, kind of questionable efficacy in terms of they can remove the plaques, but does it actually help with your long-term cognitive health? It's still a little unclear.
And is this stimulation, is it a one-time thing? Is it an ongoing treatment every so often?
Yeah, it's an ongoing treatment. So
Okay.
typically for Parkinson's, it's pretty much stimulating continuously. That's in the case of Parkinson's. There are some other indications where you can use deep brain stimulation as a therapy where it might not be on all the time. So there's actually an example where DBS is being used for epilepsy. There's a pretty cool system called the NeuroPace, which essentially is kind of like a pacemaker for the brain. So it's recording activity in the brain, and when it detects abnormal activity at the beginning of a seizure, it tells the system to stimulate and stop the seizures from occurring. So that's another example of a type of deep brain stimulation that's not on all the time and is kind of just there to try and stop abnormal rhythms.
That is just awesome. And at the beginning, you made the distinction, of course, between receiving data and inputting data. So what type of device is able to record that? Is that an implant? Is that some sort of more Neuralink style device that does that?
Yeah, it is an implant.
Okay.
So that device, I talked earlier about the current deep brain stimulation probes are these like rods of electrodes that get
Yeah.
inserted down into your brain. With the like NeuroPace pacemaker-like device, there's the rod of electrodes implanted into your brain that's stimulating, but then there's another strip of electrodes that get placed on the brain's surface. And those are the ones that are going to record seizure activity. So that system has essentially two different electrode arrays, one for stimulating and one for recording, but it's all implanted.
I do want to get into the business side of this and how you started that. But I just think it's so profoundly interesting, the concept of a symphony going on with the brain and different sets of frequencies indicating healthy or unhealthy brain function. I mean, the implications of that are just truly, truly astounding, I think. And do you think, in your personal opinion, that as you do this more, we will start to fundamentally understand aspects of how the brain works in a way that we never, ever conceived of? Because I think we know that there's a giant neural net, and we know that it's incredibly hard to mimic all of these synapses. And when people talk about, general artificial intelligence, they talk about how hard it would be to map the human brain, although not impossible. It'll happen at some point. But the concept of different frequencies is something that I had never heard of before. So do you think this is going to give us a very different insight into what the brain is doing when it's functioning well and not?
Yeah, absolutely. So I think that one of the best things that has come out of research into brain-computer interfaces over the last several decades has been we have learned so much about brain function because we are now at this point where we're implanting these high-density electrode arrays to record activity in the brain with the very high resolution, right? And that has given us a lot of insights into brain function, both in healthy conditions, but also in different pathologies. So yes, we have learned a tremendous amount from developing these technologies to interface with the brain. And that's something I've always been interested in is how do we build the device, the technology that actually goes into the brain and does that recording or that stimulation. But yes, we've learned a tremendous amount. And one thing that kind of ties into your question there is when we create these ultra high density electrode arrays to record activity in the brain, we end up recording like tons and tons and tons of data out. And there's just a massive amount of data. And what I think has really also been driving our understanding of the brain is also the advance in machine learning and algorithms and our ability to analyze that data. Because, now when we have these ultra high density recording arrays, recording at very high frequencies and getting lots of data, we've learned a lot from being able to deploy machine learning techniques and algorithms to help us understand that data a little bit better. So the two have kind of gone hand in hand, our development of hardware to record brain activity and the more like algorithm machine learning side of things.
That's just fascinating. And my ultimate dream in this would be one day a little device inside my brain could detect when I'm about to say something stupid and then just shock me into not doing it. It's like, buddy, just shut up for a second. But yeah, I mean, this is clearly the future. And, when you talk about AI and machine learning and parsing large, it's always about data sets. It's always, the quality of machine learning is solely determined by the quality of the data being fed into it. And what's so interesting about the intersection of machine learning and sources of data that we don't even fully understand is that it can detect things that a human never could. By analyzing tons and tons and tons of brain data, it forms some sense of pattern and can tell you, hey, this is a red flag for something, where no human would just look at it and say, that's just total gibberish. And that's both the amazing thing, in my opinion, about AI and also the scary thing that, the amazing thing, it'll do things we can't comprehend of. The scary thing is that we have no clue what its basis for making the decisions it makes is, right?
Yeah, absolutely. And in the field of neurotechnology and brain-computer interfaces, I think we have really started to reckon with this increase in the capabilities of AI and need to be really, really careful when we're thinking about developing new technology, not knowing what the advances in AI might be in the next few years, because there's a lot of worry that these algorithms might someday be able to, take a random data set of recorded data out of someone's brain and be able to identify who it is, right? So when we get into the medical world, we think a lot about patient confidentiality. We don't want their data to be identifiable when we publish papers using, recorded data. Right now, we have no way to identify who a person is that we get a brain signal from, but who knows where algorithms will be 10, 15 years from now. So that's something that neurotechnology makers have to be really, really aware of, and really thinking ahead of how can we build in protections for people and privacy, knowing that algorithms are getting better and better at identifying patterns, and who knows, someday they might be able to kind of pick out things that we couldn't even imagine from these data sets.
It almost seems like a foregone conclusion, honestly, that it will at some point. The question is really just when, right? And I've never had a conversation like this where privacy hasn't come up. So clearly, everybody else is thinking about the same thing. All the ethical people are thinking about the same thing.
Yeah.
So you were sparked by this passion during your education. Obviously, you went to some top universities. At what point did you decide that there was a business in this? And were you always thinking in an entrepreneurial way, or was this something that was you were forced into? How did you end up along this particular path?
Yeah, that's a great question. So I would say that when I was in grad school doing my PhD, I was developing a lot of new technology that I was really excited about. And in academia, when you develop a new technology, you write a top tier, you write a paper, you publish it in a big journal, and it's all very exciting. But that doesn't necessarily mean that it will actually go out into the real world and be used by people. And I was a little, fed up with the sense of the incentives in academia are just to publish a paper, and then that doesn't necessarily mean that your technology will go out into the world and be used. So late in my time at Penn, I actually thought very seriously about entrepreneurship and spinning out a company with some EEG technology that I had developed there. And I had a couple of faculty members who were very excited about it. And we kind of started down that path thinking about whether there was a business there. And I ultimately got a little bit of cold feet in terms of I was the only person who could have been able to drive it full time, because everyone else involved were pre-tenure, early stage faculty members who, were building their academic labs and their careers. And it was also like EEG seemed like a very crowded space. There are a lot of companies building EEG technology. And so I kind of put that on the shelf and moved on and decided to continue in an academic career path, because I also really loved teaching and mentoring. So I decided to do a postdoc. That's how I ended up at MIT. And as soon as I joined Polina Anakiva's lab at MIT, I met my colleague MJ Antonini, who had done his PhD in that lab, developing the bioelectronic fiber technology that I talked about. And he was already very much thinking about starting a company with this, because he had very much the same sense that I did of, I really like building new technologies and I want them to actually get out into the world and be useful and not just be a scientific paper that sits on a shelf. And so MJ and I worked together on a project in the lab for a year and a half, and just found that we had a really good partnership. We worked really well together. We had some of the same goals and values. And so it kind of came to a point where I knew that he was trying to build this startup company. And I decided, yeah, this is something I really want to be involved in. This is exciting. I think we have a really, really interesting technology that has a lot of potential. So yeah, that was kind of the origin story of how it came to be.
And how many years ago was that part?
That was just under a year ago, to be
Just under
honest.
a
I
year
mean,
ago. Yeah, I know it's
I've
early,
been in
yeah.
the lab for 2 years, but we officially decided to launch the startup last spring. So
Okay.
it's still pretty early stage.
That's amazing. Do you think that in academia, everything you said resonates so much with me? Do you think that generally, and maybe this depends on school to school, generally there is a pressure to go into entrepreneurship, or is there more pressure to not and just stay in the world of academia?
Yeah, that varies a lot by your institution. I was very fortunate in that I did my PhD at Penn, which definitely has an entrepreneurial focus. And they had some resources there in trying to help academics sort of translate things that they developed in the lab out into companies. Um, MIT, even more so. MIT is such an entrepreneurial place. There is incredible ecosystem here of resources trying to help scientists and students from MIT translate their technologies out into companies. So I've been really, really fortunate to benefit from that ecosystem and all the resources and mentoring that we've had access to. That said, I think that is sometimes a little bit separate from the purely academic. So if you're in your academic lab with your faculty advisor, many of them are not necessarily interested in entrepreneurship and are definitely more focused on kind of mentoring students to maybe go down the academic path. So I thought very seriously about staying in the academic path for a while, but I was, not really getting the exposure to entrepreneurship unless I went and sought out those sorts of experiences and resources.
When you finally made the leap, did it seem like a big risk to you to do that, or did it seem just like a logical thing to do?
Oh, it definitely felt like a big risk.
It probably still does. Does it
I'm,
still? Yeah.
yeah,
it's,
it still, oh,
yeah.
it still does. It still does. We're early stage. I'm a first time founder, a first time
Yeah.
entrepreneur, and there is so much to learn. And I've been really excited about going through that process and learning so much alongside MJ. I think part of the reason I was so excited to join this endeavor is that, my co-founder MJ and I have such a good relationship, and he has a lot of more experience than I do in entrepreneurship, having spent many years kind of working in that space. He hasn't started a company before, but had done a lot of programs at MIT to build up his experience in how do we actually build a business and run a business. So it definitely feels like a big risk. For a while, I was thinking about just hopping on board one of the other very cool neurotech startups that was already out there. But then I thought, let's give this a go. I think we can build our own technology into a really viable business. So
That's amazing. Well, from your website, you mentioned the papers, and from what I could see, you've published dozens of them, or several papers at least. So, is there anybody else thinking that you know of along the same lines? Are you mostly in uncontested space?
yeah, I would say that the technology that we're using, this kind of bioelectronic fiber technology, is quite unique. There are not a lot of other people working with that kind of technology because it's been pretty extensively developed in our lab. The other scientific labs that are now working with that technology are mostly people who have come and done their PhD or postdoc in Polina's lab.
Okay, right. So it's all
In
radiating out,
the
yeah.
commercial space, I would say the only one who is taking a similar approach to us is Synchron, and I'll be completely honest, we're a little bit piggybacking on Synchron. They've been in this
Okay.
space longer. What they're trying to do is build a brain-computer interface on a stent. So similar idea of going in through the blood vessels, but they're using an existing technology, the stent, and they've built electrodes onto that. So that's a really, really cool system. And they've been pioneering this idea of the endovascular deep brain or endovascular brain computer interface for almost 10 years now. They've been around longer than Neuralink. And they're a fantastic company. They're doing incredible work. They're in human trials right now, I believe. So they're the closest sort of technology to ours. That said, building theirs on a stent, their device is still relatively large. I think it's about 2 millimeters. So they can only access really big blood vessels in the brain. So one of the advantages that we have is we can make our fibers down to about 50 to 100 microns. So we can get into much smaller blood vessels. So hopefully we'll be able to target more regions.
Yeah, I have to believe that. From your perspective, in the next 5 to 10 years, what would the absolute best case scenario be, both in terms of the implications of this tech and also for you and your company personally?
Yeah, I think, it's early days for us in terms of translating the technology to human use. So we've got quite a lot of work to do. 5 years from now, if we can have already be starting our kind of first in human, that would be fantastic. It'll take some time to do preclinical testing and get through the FDA to that point. But hopefully we'll be testing in humans. And, ultimately our goal is to increase access to this therapy. This brain stimulation therapy works really well, but it's scary for most people to think about getting a really invasive procedure. And so if we can make that minimally invasive and really lower the barrier, we hope that it can reach a lot more people and really impact a lot of people's lives.
So do you think that possibly eradicating some of these diseases might be in the cards? Maybe not 5 to 10, but 10 to 20, 10 to 30. Do you think that we'll be able to wipe out a category of certain types of illnesses?
Yeah, so I'll be completely honest, I don't think brain stimulation is going to wipe out any of these diseases. What it is remarkably powerful at doing is helping to alleviate symptoms. And it's also, right now, it's in clinical trials and being explored for intractable depression, Alzheimer's, PTSD. There are other conditions that this brain stimulation type therapy has shown a lot of promise. But for the most part, with stimulation, we're often treating symptoms and not necessarily curing the disease. So it's tricky because there's always this kind of underlying pathology that's more on the cell and molecular scale that we can address with stimulation, but we're not going to cure the underlying pathology. So I think that there's, a hope in the future that there might be some combination drug and stimulation therapies that could really transform it. Whether we'll have cures in the next 10 years, I don't know, but I hope so. We can always hope.
We can always hope, right? Exactly. And along those lines, I like to sort of close things out with this question. Are you generally optimistic or are you generally more pessimistic about the future? I'm just going to leave it at that.
Oh, wow. Yes, I'm generally very, very optimistic. I'm so excited for what this technology is doing for our understanding of the brain, which I think has tremendous implications in terms of how we treat neurological disorders and diseases. For so many years, these disorders have really eluded our ability to treat them. And so many patients are left with very little hope for relief of their symptoms or any sort of curative outcome. And so I think the real boon in neurotechnology over the last few decades has really advanced our understanding of the brain, and it's starting to provide new ways that we can deliver different types of therapy to help these patients. So I'm really, really excited for what the future holds. I think it's a really exciting time in the neurotechnology space, and I think that there's a lot of advances coming down the pipeline.
How cool is that? Well, now to wrap things up, do you have any bits of wisdom? I mean, I love that you're at this particular point because you've just made the leap, and this is such an interesting time because 10 years from now, this will all be a distant memory, right? And somebody will ask you this question and you won't even remember how you felt. But now that you're right here, do you have any advice for somebody who might be taking the leap or who is considering doing something entrepreneurial to get their ideas into the real world?
Yeah, I mean, I think the biggest piece of advice that I can give is to always follow your passions. Like, if it's something that you are truly passionate about working on, then taking the leap to entrepreneurship will feel a little less scary and you'll still be passionate about what you're working on through all the highs and lows, right? Entrepreneurship is really hard. Um, it's a really difficult journey, and just having your North Star of what you're so passionate about achieving and what you're excited about working on will help you get through all the highs and lows. The other piece of advice I would give is surround yourself with the right type of people, right? With people that you love working with, have a good relationship with. That's so, so important, especially in entrepreneurship. I talked a little bit about how I had a bit of a false start in entrepreneurship during my grad school time, and it's because I didn't really have anyone who was going to work with me full time on it. And I felt very alone. And now I found a fantastic co-founder and just a great team to work with, and that has made a huge difference. So to anyone considering entrepreneurship, yeah, find what you're passionate about and find great people to work with. So important.
Well, I'm really happy to have met you and to have learned from your insights. I knew it was wild at the outset of this, but now I feel even more. I'm going to be buzzing about this for quite some time as I think about it, and it's going to really change my concept of what might be possible. So thank you for that. I wish you incredible success in these stages and the next stages. I know there's many mountains to climb, as it were, but I think you're uniquely poised to do so. And I think, again, anybody who takes a look at your website, and that's neurobionic.io, right? Everything's .io
Yes.
these days because it's input output. Although more input, .I. Skip the O.
Yeah.
.I. That's for Neuralink. And the EEG people, I guess I should say. But yeah, it's super cool. I think you're up to something really good. So let this be one more voice or just somebody this week who's just saying, good job, keep going. You're doing profoundly important work, it seems like, from my humble perspective. And yeah, thank you very much for sitting down and sharing your ideas with me.
Absolutely. Thank you so much. It's been so fun to come on the show.
Great. And with that, the official podcast is over.